It's going. Okay, we're just going to review real quick just everything for the quiz. What? What's wrong? Oh, big stink bug. Sorry.
Oh!
Okay, enough. So we're going to review real quick for the quiz here. Work and energy, right? So let's kind of go back to the beginning when we had just kind of the general definition of work. Get a brighter marker here. Work equals force times distance. So you apply a force over some distance and work is done. Right? That was kind of going back to the beginning here. Right? Kind of back to the very beginning of this worksheet. We had that block, applied a force to it over some distance, we calculated the work being done. And that equals the object's change. We said just change in energy initially, right? Individual forces will change an object's energy. Later on, we said, okay, really it's typically the change in kinetic energy. So if you see just the delta E there, which it is on the formula sheet, the equation sheet, which you probably have, I can give you one. You can use those, of course, on quiz or whatever. Change in energy, that could be kinetic energy, that could be gravitational energy, that could be spring potential energy, any type of energy that really could be. Typically, though, it's kinetic energy. Work causes objects to change with kinetic energy. So let's just look at a basic example here. Sorry, my face, that would have been epic for a video. Just a really quick example, kind of like one of those first ones we did, right? Where we have some block, let's say it has a mass of 4 kilograms, right? Let's say some force pushes it forward. All right, a force of positive 5 newtons pushes this block forward, starts from rest, let's say. The initial is 0, so the block's sitting there at rest on the table maybe. You come along, you push it with 5 newtons of force, and you displace it, let's say, delta x is 4.0 meters. This could be pushing a box of books or something across the floor maybe, something like that. Mr. Roboto moving a box of review books down in the storage room. All right, so you moved it this far, 4 meters. You know that 5 newton force, maybe it's going to keep acting, but it's going to end up with some final velocity, right? It's going to have to gain kinetic energy. So the first thing I'm going to ask you here is, what is the work done on the box of books? What's that? You guys are quick. Work equals force times displacement. So the force is 5 newtons of force. All right, so already here, 5.0, and it's positive, right? The positive sign matters. Displacement is positive as well. All right, 5 newtons times 4 meters, 4.0 meters, you get positive 20 newton meters, which, remember that was what a joule is. 20 newton meters is 20 joules. So, you gain 20 joules of energy. The work done is 20 joules. The box would gain 20 joules of energy. So that's kind of where we started. And then what do you think the next thing I would ask you would be, based more on kind of what we did yesterday and those problems we did while I was out there? What would be the next thing I would ask you?
Final velocity.
Right, final velocity, final speed. All right, so we have this other equation here, right? Kinetic energy equals 1/2 the mass times the velocity squared. These are the two important equations here, kinetic energy and the work. So if I was to ask you for the speed now, let's say this was part A. All right, let's say part B here is the final speed. Right? That's what we were doing yesterday. We already did, I was just giving you this number yesterday, right? I said a force does 10,000 joules of work on an object, determine its final velocity. Well, now I'm saying, okay, we calculated it here, all right? So if I want to figure out the final speed, I can say, okay, the change in kinetic energy has got to be 20 joules, right? It's got to gain 20 joules because it's speeding up. So if it starts from rest, that means its final kinetic energy is going to have to be 20 joules. So if it starts from rest, right, the initial kinetic energy is 0, it gains 20, so the final kinetic energy has to equal 20 joules. So 20 joules has to equal 1/2 times the mass, 4 kilograms, times d squared. So everybody kind of had, in my other class, people were taking 1/2 of the 4 first. They wanted to do that, which is fine, right? I usually multiply both sides by 2 and then divide out the mass. Some people were taking half of the mass first and then dividing that out. Doesn't matter which way you do it. So I'm going to do my usual thing here, multiply both sides by 2. So that cancels out the 1/2 there. And then I'm going to divide both sides by 4. All right. So I get 2 times 20 is 4, right? Or 40, sorry. 40 divided by 4 is 10. I'm going to drop the units here. So 10 equals d squared. Then what's the final step to get the velocity? Take the square root of both sides. Good job, good job. Whoever said it. Square root of 10, what is that? Like 3 point something? 3.16, so what did it say? 3.2 meters per second. That's the whole point of this work, to, have a force over some distance and ultimately be able to get to the final speed. All right, there's other ways you could do this using Newton's second law, but this ends up being easier. So just to kind of recap, we had this block, we had a 5-Newton force acting on it over 4 meters. That means that force did 20 joules worth of work on it. That 20 joules worth of work, that causes the energy of the block to increase. All right? So that 20 joules of work causes kinetic energy to go up by 20 joules. So your final kinetic energy is 20 joules. That means the object must be moving at 3.2 meters per second because of its 4 kilogram mass. If it was a smaller object, if the mass was less, then it would end up moving faster. If the mass was more, it would have to move slower. All right? That kind of ties it all together there, what we're looking for here. Questions on this one? Questions on this one? I will always give it to you in steps like this. I'll say part A, determine the work. Part B, determine the final. That gives you the framework, how to do it. Okay? Do one more here. There's one I kind of did with my second theory class. Oh no, I didn't get to it. I did it with you guys, basically. But I wanted to get another version of it on film here for kids at home. That one where we figured out the approximate change in energy. Work done in bringing a car to rest. I think we kind of estimated that yesterday as a class. But I want to get that one kind of formalized on video and as an example because that's an interesting one to think about. All right, so the example is we have let's say it's a little bit bigger of a vehicle, maybe it's a van or something, right? Let's say its mass is 3,000 kilograms, all right? Its V initial, let's say, is 15 meters per second, so it's going this way. It's moving 15 meters per second. let's say it approaches a stop sign, right? Approaches a stop sign, they hit the brakes, and it slows down so that V final is 0 meters per second. So they give you the mass, they give you the velocity. The question is, how much work, part A, how much work must the brakes do? Now, you got to be careful here, right? Because if you're just purely looking at the equation sheet and you say work equals force times distance, well, I don't have a force and distance here, right? I could give you a distance. Let's say it takes, say it takes 20 meters to stop. Well, I still didn't give you a force. So you can't use force times distance. This is where you have to recognize that change in energy is also work. So we got to figure out how much the kinetic energy is going to change by, right? So where should we probably start here? What do we need to figure out first? What do you think?
Figure out initial kinetic energy.
Right, you got to figure out how much kinetic energy you're starting with and what's going to happen to all that energy. What's going to happen to that energy? What do you think? What's going to happen to that energy to start off? What's going to happen to it all? You lose it. You lose it. Where does it go? Into the brakes. Literally the thermal energy of the brakes. They get hot. All that kinetic energy of the bus goes into the molecules that make up the brakes, them vibrating and getting hot. Goes from actually one form of kinetic energy into another. It goes from kinetic energy of the bus into the kinetic energy of the molecules in the brakes. It's kind of a mind bender, isn't it? Anyway. Yeah, so the work equals change in energy. In this case, it's change in kinetic energy. So a change in kinetic energy, it's always, any change in anything is always the final kinetic energy final minus the initial kinetic energy. So change in anything is always final minus initial. Well, we know the final is 0, right? So we end up with this. The work done equals negative 1/2 mv squared. It's negative because it's going to be losing this energy. If you just figure out the initial kinetic energy, that's fine. Right? And I'm not going to be a stickler about the signs here, but you should know that they do matter. Mass is 3,000 kilograms. Initial speed is 15 meters per second. That's going to be squared. All right. Liam, did you already plug this out? What'd you get? Jack? 337,000. Wow. So the work done is 300,000. What was that? All right. Can you read it again, please? 337,500 joules. You can get big numbers like this. You do.
Why is the half negative?
I made it negative simply because of this equation here. If you find the initial kinetic energy and tell me it's that, I'll take it. I don't care. That's fine. I just did kinetic energy final minus kinetic energy initial. So kinetic energy final was 0 because it stops. So you have 0 minus the initial kinetic energy. So that negative sign, it's there for a reason. It's not magic, right? It's there because it's telling you that energy is being taken out of the object.
Yeah.
That's what a negative sign means. It means taking energy out of the object.
Can you also turn the W into a KE?
Yes. Yep. Work equals change in kinetic energy. Work and energy. Work is the change in energy. That's the definition of it. Technically speaking, but I'm not going to be a stickler. The work, the work done is 375. It's taking it out, though. if I ask you a follow-up question, which I don't have to quiz or anything, say, okay, is that work putting energy into the object or taking it out? You could answer that just from kind of thinking about it, right? Now, if I want to take this a step further, I would say, okay, all right, how much force must the brakes apply? What must the force of the brakes? All right, so this is kind of the reverse of the last problem. So if you know that the work has to equal force times distance, right? If you know the work has to equal force times distance, you know that the work is 337,500 joules. That has to equal the force times the distance. It took 20 meters to stop. Right? It took 20 meters to stop. Well, just divide by the 20 meters. And remember, joules and Newton meter. So the meters are canceled, this is going to give you a force. So that divided by 2 is basically, I don't know, 170,000 or so. So it's probably 17,000 newtons or so, the force acting. What is it actually divided by 20? You got it in Kevin? 16,875. Okay, 16,875, so. 16, 9, 3 sig figs, 2 sig figs, it would be 17,000. Which is typically all we need.
How'd you know 20 was...
Well, I gave that to you initially. I just kind of said, okay, it stops over a distance of 20 meters. So you're dissipating that energy over a distance of 20 meters.
So that would be always delta x is distance.
Yeah, delta x is the distance it takes for it to stop. What are you giving up on? Don't worry. You'll be all right. So